I think that you are already seeing my screen, I think. Can you confirm it, please?
Yes.
Yes. Okay, thank you. I'm going to try to make a wide overview of the work that we have been developed on the topic of Portuguese vernacular architecture, and to give you some points on many topics regarding energy and regarding materials and comfort conditions, etc. Just a brief introduction to the topic. So what do we understand by vernacular? Usually we use the definition that is already on the Charter of the Built Vernacular Heritage. So it is a fundamental expression of a culture of community in the relation with its territory. In a traditional and natural way of the communities to build or to construct, and a continued process of evolving and adaptation to the social and environmental constraints. And this will be visible on the topic that we are going to show now. So the line of evolution of vernacular construction has two main points. The first with agricultural revolution, and the second with the industrial revolution. On the part of the agricultural revolution, when the man settles down and became a farmer, he has the need to build his first permanent houses. And it's here that starts this evolution and this adaptation to different territories and different climate conditions. And that's why we see so many different manifestations of vernacular architecture around the world. As we see the kind of the igloos or the wind towers on Iran, or the buried houses on Tunisia, and also the courtyard house from the Romans, etc., and many other examples that we can express here. This is just a quick introduction. And with the Industrial Revolution, this line of knowledge, of empirical knowledge, was broken with the rise of this new standard and industrialized building materials. So glass, steel, concrete, etc. These kind of materials start to homogenize the way populations build their buildings, and the buildings became a little bit all the same. And we can see that and express that, for example, with the buildings from the modern movement, where they argue that this kind of architecture should be applied all over the world. Now we know that this is a mistake. These buildings do not have good comfort conditions. You can see here a lot of glazed areas, very weak thermal behavior. And this all was only possible because of the, can I say, free energy available. Fossil fuels were not a problem, carbon emissions neither. And so the buildings were very dependent on mechanical systems to ensure comfort conditions. And also the buildings became very technological on the part of they rely a lot on the technical systems to operate. And we know that we have to change some of these things if we try to be more sustainable. Now we are in the beginning of a third revolution, if we can name it like that. That is a sustainability revolution. For some cases, the term sustainable is already outdated, because we have to be more than neutral on the impacts, but now we have to be positive and compensate all the negative impacts that we have caused in the last decades. And this implies a new way of thinking. We need to think differently, and the building sector is a key sector to implement these strategies, because it has a lot of impact. We all know that is responsible for more than 40% of the energy use on the building stock, is also responsible for more than a third of the carbon emissions, and it's also responsible for the more than 50% of the raw materials used. So it is a building sector with a lot of environmental impacts, and is key sector to implement new strategies. As an example, one of the most famous directives from the European Union, with the goal of mitigate some of the problems that we have mentioned, is the Energy Performance Buildings Directive. Yes, define ambitious goals on energy efficiency, energy reduction, and the reduction of carbon emissions, has also defined new standards for buildings as the nearly zero energy buildings. And as the buildings became more energy efficient, other problems arise. To touch in another topic, we can see here, for example, that for a conventional building, the embodied energy of the materials represented only 10 to 50%. But after the implementation of the Energy Performance Building Directive, as buildings are more efficient, we can see that the percentage of embodied energy will be considerably higher. So now we have also the discussion how to have building materials that are more efficient on the part of the embodied energy, etc. On the topic of the energy, this is a diagram developed by Stefan Belling from the Foster and Partners office, and he proposed this definition of sustainability based on these three items: architectic form, passive systems, and active systems. And they say that today we give too much importance to the active systems, so the building depends on this to operate. That in the future, that we call it now the present, we have to invert all this triangle and put more emphasis on architectonic form. Here architectonic form, not the part of the aesthetic, okay, the part of the function more, and rely in the part of the passive systems, and active systems should act only as a backup to the building, only when they are needed. And we had a new triangle to this diagram representing the past, because in the past buildings do not have electric power to operate, so they relied only on architectonic form and passive systems. So some of the strategies that we find in some buildings of the past could be interesting to implement in the change that we need to operate. And why vernacular buildings are so interesting? Because in the pragmatic way, they condense in themselves a lot of constraints, as the climate, geography conditions, also the economy of the communities, and also in history and cultural issues. And this is continued to be a topic that raises interest all around the world in many countries. Every day there is a new paper around vernacular architecture, and there are some interesting findings even in different papers from different regions, that, for example, that vernacular buildings can achieve acceptable comfort conditions throughout much of the year, just using passive strategies, that were technologies developed in response to specific climates, that vernacular materials that have low embodied energy and low environmental impacts. Often these materials are biodegradable and can be classified as a cradle-to-cradle material. And we need to try to use the best of the technology that we have now and try to merge with some of the low-tech strategies they had at the time, and improve these techniques. And most of the strategies or sustainability principles that we find in vernacular architecture, as the use of the soil, heating passive strategies, passive cooling, use of local materials, renewable energies, rainwater harvesting, etc., are the basis what we call now the sustainable construction. And just to give you an example, for example, for Portugal, we can see that in this simple example that most of the passive heating strategies are located in the coldest regions of the country. We can see here, for example, the glazed balconies. That is an interesting passive heating strategy for indirect gains, and I will show an example after. That is being used, for example, in Austria as a refurbishing strategy for buildings. So it is interesting on that point. And for example, for passive cooling strategies, most of these strategies are concentrated in the southern part of the country. So the strategies and the climate have a lot of influence here. And for example, in this example, in the monitoring that we carry out in 2007 in Évora, in this courtyard, in a peak temperature during the summer, the temperature in the courtyard was 9 degrees lower than in the city center of the city. So we have a passive strategy here that creates a microclimate in the house that is possible to ventilate and cool the house in a natural way. But also the use of light colors to reflect radiation, the use of strategies, for example, to overnight cooling that is particularly relevant on these hot regions to remove the thermal loads that were gained during the day, but also at the urban level with very narrow streets, allowing that a building shade the other, and also the use of very simple shading devices, as we can see here with this vineyard. These are just a few examples I'm trying to show you very quickly, since we do not have so much time. So what were our questions regarding Portuguese vernacular architecture? Because most of the studies were mainly qualitative. So we need to quantify the performance of this. So how effective are vernacular passive strategies? Are they really effective? So are vernacular materials sustainable, in fact, and what is their potential nowadays? So we divided the work in two parts. One, monitoring the thermal performance and comfort of different buildings, and the other part on the life cycle assessment of vernacular materials. On the first one, so we measure and gather data for the weather data from outdoor conditions, and indoors we measure temperature and relative humidity, and also use the specific equipment to measure other parameters that have influence on the comfort, for example, as mean radiant temperature, wind speed, etc. And we have surveyed the occupants to know if they are comfortable or not, because that part is important to cross-relate the quantitative data with the opinion of the occupants. So we have been working on 3 different climate zones by contrast. So one in the coastline, the other one in the north part of the country, and the other in the south. So the 3 different type microclimates that we have in Portugal, but also trying to address different ways of building. For example, in the coastline, we focus on the timber buildings, on the northern granite buildings with the glazed balconies, and in the south, earthen buildings, and also the passive cooling strategies they have. I do not have time to present the 3 and the other case, that new cases that we have now. So I'm going to focus very quickly on these 2, and particularly on the other one in the south, since we are talking also about Montfort, and the climate of Montfort is similar to the one to the case study in the south. This is the first example. This is a very small building in the municipality of Taboas. This is a building that was refurbished recently, and so this is the behavior of the glazed balcony during the summer, acting here more as a ventilation strategy to push the air through the building from the coldest part of the building in the north part, in the north of state, to the south, and during the summer, during the winter, acting as a indirect solar gains system, and it works very, very well. Usually this kind of glazed balconies were well oriented between south and west, because the number of hours with more intense radiation, and this is a very relevant fact. And just show you some of the results of the simulation for this building in specific. And the building that has the glazed balcony, or the room that has the glazed balcony, the energy demand for heating and cooling of this room was, according to and depending on the comparison, 25% lower or 35% lower than the buildings without a glazed balcony, or without with lower glazed area. So this strategy works if it is optimized and well oriented. It's a very interesting strategy to consider in the north of the country. And we can see here also that during the coldest week from the weather data, that in a free running mode, the building, we can reach very high peak temperature peaks inside the balcony. You can see here, for example, when outdoor temperature is below 10 degrees, we can reach a peak temperature indoors above 25. So these are very interesting solar gains. Going south, this is the building, Raymond Earth building. Is located in the municipality of Moura. This is located in a village that is roughly 5 kilometers from Malaysia, that has the record for the highest temperature recorded in Portugal. That was 47 point something. This is a Raymond Earth building with very thick walls, around between 60 and 80 centimeters thick. Okay. It is a lime washed building to reflect radiation. It has this ventilation parts for overnight cooling without compromising privacy, etc. It is located in a compact urban layout. You can see here that most of the buildings have patios, so it is a very important cooling strategy in this area. The building is organized in a very simple way. So in the north part, we have the bathrooms and the kitchen, and in the southern part, we have the living areas as the living room and the bedrooms. These are some pictures from the building. As you can see here, for example, those of the vaulted ceilings, the use of these ventilation shutters on the top of the windows and doors to promote ventilation without compromising privacy. And this is the only, if you call it, active system they have in the building, and it is only for heating. It does not have any kind of cooling system or an active cooling system. This is the results from the summer monitoring. And as you can see here, for example, in most of the days, we have temperatures above 35 degrees. In some days reaching 40, and indoors the temperature is almost flat, around 26 and 27 degrees. The green line that you see here is the attic. That's why it's more close to the 30. So it has a very, very good thermal behavior due to that huge thermal inertia that the building has. So it has almost no temperature fluctuations during the summer season. Regarding relative humidity, this building has also very interesting results because relative humidity is most of the time between 60 and 40%. That is the most adequate range for comfort, human comfort. And applying here adaptive comfort model, we can see here and explaining briefly, for example, if our thermal sensation is above this line, will be hot, and below this line will be cold. And you can see here that for a building without any kind of cooling systems, we have the comfort range in the middle, so a perfect thermal condition for a building that is from the end of the 19th century. On the winter part, this is not so good, okay? So we can see here that we have in most of the compartments, we have a comfort temperature below the 18 degrees. But also this is a building that is not heated 24/7, okay? You can see here the peaks between, for example, 6 p.m. and 11 p.m. You can see here the peaks that we have here. But for example, when you have 2 days in a row where they were heating the building, when they left the building for a couple of days of vacations, the building take almost 4 days to reach or to descend to the temperature of the other rooms. So the thermal inertia of the building is also has also a very relevant behavior on this topic. Also in the part of the relative humidity, even if outdoors the relative humidity is frequently above 90%. You can see here that due to the hygroscopic properties of the ray earth material, you have also very good results on the relative humidity topic. On the part of the thermal comfort, it's not possible to reach a thermal comfort condition without using the heating or that kind of the fireplace. But with the fireplace, it's very easy to reach comfort conditions on that topic with a very simple system. In this case, we apply the categorization, use the standard of the 15251 in order to try to understand in each category the building is and to compare this building with others. For example, to clarify what is the categories. Category 1 is the category for the most demanding buildings, in special buildings, as for example, kindergartens, elderly homes, etc. And category 2 is the requirements for new buildings, and category 3 is the requirements for existing buildings. And out of this will be category 4, out of the boundaries. And we can see that in the quality of indoor thermal environment during the winter, most of the time the building is on the category 4, it's out of the boundaries, since the building is not heating in permanence, etc. Regarding the part of the humidity, the results are quite satisfactory for this. But what is more interesting is that during the summer, in the building that has no mechanical cooling system, the building is most of the time in category 1, the most demanding category, for the part of in the part of the thermal environment, but also in the part of the humidity during the summer. It's most of the time in category 1 and category 2, just with passive means. And we also did some simulation with this building. At the time, we will try to compare the performance of this building with the requirements of the regulation in force in Portugal. So at the time, for that climate zone, the maximum U value was of 0.50. So it was very low. So it was impossible to build a building with ramed earth without using thermal insulation, as you can see here, because the minimum and with the 1 meter thick wall will be 0.87. Now it is allowed to build with 1.40. The new regulation in force is allowing now to build without thermal insulation. So, but consider the study. We try to compare the same building, changing only the external walls from the envelope. As you can see here, the traditional ramed earth wall has the worst performance on the annual energy demanding for heating and cooling. Is the worst. But there is something here that it is interesting, because in the part of the cooling, this wall is the best one. Probably is roughly half of the double brick cavity wall, and roughly a third of the brick wall with the attics. Okay, so what we can read from this, that these buildings were conceived particularly to deal with summer climate. This was the most difficult issue to solve, and they work very well on these conditions. In the part of the winter conditions, we need to improve some of the systems and see how can we improve the behavior. But the part of the cooling is very important, because regarding the International Energy Agency, until by 2050, the energy demand for cooling will be the triple. So probably some of the conditions that we have on this simulation, if we put the scenarios of the climate change, probably these values will change also. And this kind of strategy could be more interesting to apply. Regarding the life cycle assessment, and to conclude, we try to see from the traditional materials which were the ones with the most potential to be applied nowadays, and that where we can find some of the companies already specialize on this. And we select ramed earth and compressed earth blocks as a kind of improved adobe. Okay, We went to a private company specialized on this. We did the life cycle inventory, and we applied the standard for environmental product declarations. Why? Because there were many studies assessing the life cycle assessment, we can call it like this, of Raymond Earth, etc. But they were not using this a standard. Sometimes they compare a topic, in the others another parameter, and it was very difficult to compare these materials with, for example, with conventional materials. It was almost impossible. So we developed this according to the standard for APDs. So this data can be fairly compared with other materials. So what we take into account, we take into account all the product life cycle, and considering extraction, processing, and production, etc. And in the case of this earthen materials, since they have the potential to be reused or recycled with exactly with the same function and without any kind of processing, of complex processing, we have also included scenarios, end life scenarios for this. We take into account all the inputs of resources, materials, energy and water, and also take into account emissions and waste. Sorry. In the case of the compressed earth blocks, we consider the stages from the extraction to the gate of the factory, because beyond that we do not control. And in the case of Raymond Earth, since it is building on site, we have considered also the stages of transport and construction on site. Okay. We defined some scenarios, end life scenarios, but we have not taken into the calculation the impact of that, because it was very uncertain. Trying to make here a fair comparison with other conventional materials. For a square meter of wall, we compared the compressed earth blocks and the Raymond Earth walls for the same requirements. Okay, for the same requirements. For example, in the case of Raymond Earth, all these walls have the same U value. Okay, on the case of the CEBs, we have not considered any kind of requirement. We consider as it was only for partition walls, and it's very simple to see that only in two indicators, as global warming potential and embodied energy, the earthen materials have considerably lower environmental impacts than the conventional or industrial based materials. The difference is very clear. If we put in comparison all the other indicators, as you can see here, in this case the CEB ones in most of them, and also here for the Raymond Earth the same. So the difference in all the environmental indicators is very, very relevant. One interesting thing is when we try to understand by the percentage of impacts by process and module of life cycle assessment. And just an example, for example, consider the global warming potential. In the case of the compressed earth blocks, in the part of the manufacturing, more than 80% of the impacts are associated with the addition of lime to the mix. And the addition of lime in the case of the CEBs is around 6 and 70% of the block. But these 6 or 7%, only these represent more than 80% of the impacts of the blocks on this part of the manufacturing. And regarding the part of regarding Raymond Earth is roughly the same, but in this case we have two other parts. 60% is for the lime, that is only 3% of the Raymond Earth mixture, but we have also the part of the fossil fuels from all the equipment that they use. For example, the Raymers, because they use a power generator that is powered by fuel, so the impact is here, and all the machinery as the mixer, etc., that run on fuel. And so we have the impacts of this. If we can reduce or be more efficient in this kind of energy, we can improve even more the environmental impacts of these materials. And just to conclude, we are going to launch briefly, I think, or I expect, a new tool from the project that is called the Rever Atlas. And it's going to be Atlas and with a map where we can find many of vernacular buildings that can be mapped with the specific strategies, where we can correlate some strategies of the buildings with, for example, with climate data, with geological data, etc. That can be, or we think it will be very useful for designers to plan and gather some information on specific passive strategies and local materials. And it's all for today. Thank you for your time. If you want to call me or contact me, my contacts are here, and please follow us on our social network to know more about the project. Thank you.